Let's share. Just share the screen. Okay. Infinite repeat. All right, let's get started. Yes, I am on campus. First off, can everybody see the PowerPoint? Okay, good. All right, so yes, I am on campus right now. A little background. So this image here I took. This was in my neighborhood. There's a transformer that was out in my neighborhood, and what happened was it was arcing and flashing down the road. This is down the road from my house, and then at about 8:30 this morning, the power was flickering on and off, and I was like, "Ooh, snap! What am I going to do?" So I got in the car and I headed to campus so I could do the lecture here. So I'm in here in our old classroom in room 1105 by myself. It's almost a little stranger than doing it from my house. But we're going to keep on trucking. Let's just sort of get right into it. Homework 7.2 was graded. The solution was posted. Hopefully, everybody was able to use the solution to complete their homework 7.3. The idea was that a lot of those sort of key values were recomputed. In order to do 7.3, you needed some values that you had already computed in 7.2. So I figured, why don't I just go ahead and post the solution, make it a little easier for you. I'll go ahead and also tell you that the serviceability stuff that we've done this past week, the things on effective moments of inertia and deflections and long-term deflections, I'll tell you that is without a doubt the most in-depth thing that we're going to do for the rest of the semester. I think from here on out, you're going to find that what we're about to do is pretty simple and pretty straightforward. Given my setup today, I'll go ahead and tell you I may have to flip back and forth between the slide and the notebook a little bit more than I would like, but I don't think it's going to be that difficult and that comprehensive. So let's just sort of get right into it. We have two more topics left for the rest of the semester, and one of those is the concept of development length. Now, development length is a little unique from a topic perspective because we're not really talking about loads or deflections or analysis. There's no moments, no shears, nothing like that. Development length is nothing more than a distance measurement. So it's pretty straightforward in that there's no analysis. But maybe I should sort of talk about exactly what development length is. So I have here on the slide on the bottom right, I have an image of a cantilevered beam. Okay, and so let's say I have this beam. So I've got the column supporting it, and I've got the beam sticking out, and the beam is seeing some sort of load. Now, let's recognize that if I have this beam and I bend it, it's going to bend sort of in a frowny face, negative moment fashion. And what's going to happen is the worst case bending, the worst case umph on the beam is right there at the support where the beam and the column connect with one another. Now, if I had terminated the rebar at the interface between the beam and the column right there where the beam and the column touch, I can go ahead and tell you that the beam would fall down and probably kill somebody. Because in order for me to be able to use this rebar to be able to resist this load, I have to embed that rebar a certain depth into the adjacent elements. See, when we design, we assume that there's this perfect bond between the reinforcement and the concrete. In other words, we say that the concrete can reach 0.85 FC prime, but the steel can reach FY. I mean, think about that. I mean, we're saying that the steel can reach 60,000 PSI. That takes some oomph. The way that I sort of describe it when I'm first talking about development length is I talk about it as if I'm talking about a tug of war. So if I'm talking about a tug of war and I've got myself on one end and let's say you're on the other end and we're playing tug of war, you have to have a certain amount of rope to be able to grip and play the game. In other words, if I'm playing tug of war and I'm grabbing here and grabbing here, I have to have a certain amount of rope to be able to play that game. So I need a few feet of rope to grab the rope. If you were to give me if you were to tell me to play tug of war, but you said, here's the deal, you can play tug of war, but I'm only going to allow you to hold 1 inch of the rope. That's all you can hold is just 1 inch. It doesn't matter if I'm the Incredible Hulk or not. I'm not going to win that game because I just don't have enough rope to grip that rope and to develop its full strength. So what we have to do is we have to embed that rebar a certain distance into the adjacent element so that we have enough grip on the rebar so that it can develop its full capacity. In other words, it's got to be able to reach Fy. And so that length, we call that the development length. So we have to embed it far enough. Now, what is the development length? How do we compute the development length? Well, here's the equation. And I'm sure that you see this equation and you're like, oh my God, that looks horrible. I promise you, of all the topics that we cover in this class, this is arguably the easiest concept that we deal with really this entire semester. Development length is computed using the yellow equation that you see here. Okay. Now it looks like there's a lot going on, but let's take it one step at a time and let's see if we can identify what these terms are and how to compute them. Now, first off, no matter what you compute, LD is never taken to be smaller than 12 inches. So you have to at least embed that element 12 inches. That's sort of a staple of the computation. All right, so let's look at some of the variables. Well, I see an FC prime in there. So FC prime we should all recognize. I see Fy in there. We should all recognize that. Lambda, our lightweight aggregate factor. There's the D sub B. That's just the diameter of the rebar that we're considering. So that's pretty simple. A couple of the new measurements are this C sub B term and this KTR term. Okay. Now, for those of you that are in steel design, I'm going to go ahead and tell you that we're going to have a lecture today in steel design, and the entire focus of that lecture is about a term in steel design called C sub B. It is absolutely not the same thing as the bar cover in concrete design, and that'll become clear after steel design. I just wanted to mention that. KTR is a transverse reinforcement index. Don't worry, we're going to go through all of these step by step. And then we have what really is sort of the really new part are these psi factors, the ones that look like the little the Greek letters, the ones that look like the little pitchforks. There's 4 of them associated with development length. I'll go ahead and tell you this is a slightly new equation than the last spec. The last spec only had 3 of them. This psi sub g, the one on the end, that's a very new one. Here, let me zoom into the equation a little bit. You all should be able to see this a little better. So yeah, so here's the equation. This psi sub g value, that's a little new for this year, for this new code spec, but it's not hard. In fact, none of these factors are hard. They're really just lookups. The only other thing to keep in mind when you do this calculation is that your C sub B, this denominator here, this C sub B plus KTR over dB, this pile of junk in the parentheses, we call that the confinement term, and that confinement term can't exceed 2.5. When you're doing these calculations, you might find that it is above 2.5, but you can't allow that to exceed 2.5 in the calculation. And then also this product here, this product of psi sub t and psi sub e shall not exceed 1.7. And that usually only happens in very, very weird cases. But that'll become clear when we get into what these terms are. What I want to do is I want to look at this equation and I want to take each of the terms that are new that you've never seen before, and I want to talk about what they are and what they mean. And there's really no math involved in computing a lot of these. A lot of these are just observational terms. So let's take each of these one at a time. And let's start off with these psi factors. Okay. So let's start off with psi sub t. Psi sub t is what's called the casting position factor, but a lot of times you'll really never hear it called the casting position factor. Instead, it's usually called the top bar factor. And the reason why we have this is let's keep in mind what development length is all about. We're trying to determine how far to embed a piece of rebar into an adjacent element to develop its full capacity. So we're trying to figure out the depth of embedment. And so what we found is that during tests, we found that the bars that are on the top, don't really bond as well as other bars. Now, that has nothing to do with the moments or the loads. It's literally the bars on the top. And there's a couple reasons for that. When you place concrete, so for those of you that have ever been on a construction site or ever been involved with placing concrete, you should know that you're placing concrete. You're usually using a concrete vibrator to vibrate the concrete to make sure that it fills all the nooks and crannies of your forms and in between your rebar and whatnot. And so what happens when you place concrete and when you vibrate, what happens is a lot of the air and the water in the concrete can sort of rise to the top. And so what happens is that water and that air, it can get caught under the bars that are kind of on top. And so the bars that are on top, they don't really get the best concrete to bond to. Also, the concrete that's on the bottom of the placement might settle. So if you've ever, remember, concrete is a mix of gravel, sand, cement, and water, and sometimes your aggregate might want to settle to the bottom. So the concrete that's on the bottom might have a little bit more oomph to it than the concrete that's on top. So what we do is we look at the casting position factor, or in order to handle this, we look at the casting position and we look at this image right here. And we basically consider the dimension that you see here below, that arrowed dimension. And what that is the distance from the very, very bottom of the beam or the column or whatever we're looking at, the very, very bottom to the bottom of the rebar. And if that dimension is more than 12 inches, we use a casting position factor of 1.3. Otherwise, we use a casting position factor of 1. That's a general point I want to make about a lot of these factors. The default value for a lot of these factors is 1. Okay. Whenever the value is larger than 1, what that means is that we need to embed the bar further to account for some odd scenario. So if we're dealing with the bars on the top, we got to embed them further. In this case, we have to embed them 30% further, or 1.3. So that's something that I wanted to mention about a lot of these factors. What about the next one, psi sub E? Okay, so psi sub E is the bar coating factor, but a lot of times we just call that the epoxy factor. If you've ever been on a construction site, specifically if we're talking about like a DOH construction site or anything where you have a concrete placement gone on outdoors, it's very common that you'll see rebar that looks like this. Let me zoom in a bit to where everybody can see. If you ever see rebar that has this sort of like light green look to it, this is rebar that has been coated with an epoxy. It has sort of like a rubbery, slippery feel to it. And we do that because, I mean, there's a lot of parameters you got to consider. And whenever you're casting concrete in the field, one of the things you got to deal with is corrosion. I mean, for instance, we're in West Virginia right now. In West Virginia, when you cast concrete, if you're talking about a concrete deck, well, what do we put on our concrete bridge decks in the winter? We put de-icing salts. And so de-icing salts, metals don't really go well together, and that causes corrosion. So a lot of times you'll find us coating our rebar with epoxy, but that causes a problem on the development length side, because on the development length side, if we have rebar that's coated with epoxy, it's slippery. And so if it's slippery, we have to embed it further. So have here a similar table. So first off, if we're ever dealing with uncoated bars or old rebar, we use an epoxy factor of 1. If we have an epoxy coated bar or a bar that is coated with an epoxy, we either use a value of 1.2 or 1.5, and the difference is whether or not we have a situation with little cover. And remember, what is cover? Cover is how much concrete is between your bar and the outside surface. And so if we have a bar that has light cover, or in other words, cover less than 3 bar diameters or clear spacing less than 6 bar diameters, then we're going to need more embedment in order to develop that bar. I want to make sure that the recording's going on so far so good. Is everything coming through clearly? This is a little bit of a unique interface for me. Somebody in chat, let me know if the audio is coming through. Good. Okay. So I will keep on trucking. All right. Size sub S is the bar size factor, okay? So let's go back to beam design when we would select reinforcement patterns. So that is a typo. That's supposed to say reinforcement. Sorry about that. Okay, so let's go back to beam design. So you've got a beam and you're doing the math. You're saying, okay, here's the factored moments on it. Here's the required moments on it. And then we do a bunch of calculations to get a rho value, a reinforcement ratio, and then we get a required steel. So we do this math and we compute like the required area of steel is, I don't know, 3.67 inches squared. And then we go to our rebar chart and we try and pick a pattern that has the smallest area possible but bigger than the required area of steel. Everybody in here should be pretty familiar with that. So let's say we're doing that, okay? You could actually go about that one of two ways. For instance, you could go with a whole bunch of really tiny bars or a small number of really big bars. And so to give you kind of an example, I just kind of wanted to just throw some numbers on this. If you go to that rebar chart, if you look at 8 number 4 bars, 8 number 4 bars have an area of 1.57 square inches. Well, 2 number 8 bars also have an area of 1.57 square inches. So there is the exact same area of steel. Now, in beam design land, what we would have said is go with the fewer number of bars. And to be crystal clear, I am always recommending that you go with the fewest number of bars because it's the same, tonnage of steel for that given problem, but fewer bars means less stuff to handle. But the point I'm making is that you have a couple of different options. Well, how does that affect development length? Okay, well, this is sort of an interesting thing with development length, but there's actually a benefit to using what I'll call small bars. And so let me sort of explain what that means. All right, if I look here at the 2 patterns that I've shown here, so I have 8 number 4 bars and 2 number 8 bars. Okay, they both have the same area of steel, and that's true. So so they both would affect the moment capacity in the same fashion. But there is a very unique difference between these two, and that's their surface area. So if you were to actually compute the surface area of each of those bars, like 8 number 4s versus 2 number 8s, what you'll find is that it might be the same cross-sectional area, but the surface area, the amount of area surrounding the bars, the 8 number 4 bars, they have more surface area. Well, reason why that's relevant is if I have more surface area, I got more bar area that grips the concrete. So when you're using small bars, you can actually reduce the amount of length that you need to embed into the concrete because you have more of them. The idea is, well, I got a whole bunch of bars, so I don't need to embed them as far. And the specifics of it is if I'm ever using bars that are number 7 and larger, I can use a value of 1, but if I'm ever using number 6 or smaller, I can use a factor of 0.8. Remember, if the value is larger than 1, it increases your development length, but if it's smaller than 1, it decreases your development length. And so what we're doing here is decreasing the development length based on the fact that we're using small bars, okay? So we've done size sub T, we've done size sub E, we've done size sub S. What about size sub G? This one's brand new, okay? This one just came into the code. It's a little counterintuitive, but let me sort of explain. So I'm zooming real far into the equation because I kind of want to make this point. So if you look at the development length equation, one of the parameters that you'll find is relevant is Fy, okay? And that makes sense if you think about it because you're asking yourself, well, how far do I need to embed that bar to reach its yield strength? Well, so its yield strength obviously is important, okay? So we've been using like a very, very common value that we use for yield stress is grade 60 rebar. Okay, so let's say that we've got grade 60 rebar, and then let's say for the purposes of discussion, I just want to use some simple numbers. Let's say I've got grade 60 rebar and grade 30 rebar. Grade 30 rebar doesn't really exist, but let's just say that. So I've got rebar with 30 KSI and rebar with 60 KSI. You would think that if I've got grade 60 rebar that I'd have to embed it twice as far than the grade 30 bar. the FY doubles, so you think the development length doubles. Well, it actually doesn't really work out that way. If your yield stress, let's say, doubles, what sort of happens is your development length actually increases more than that. It's almost like if your yield stress doubles, your development length triples or something like that. So what we do is when we have like really high grade rebar, like grade 80 or grade 100, we actually have to bump up the development length even further to account for that. Now, again, the standard value is 1, the default value is 1. So so in most cases, we've got a reinforcement grade factor of 1 when we're dealing with grade 40 rebar or grade 60 rebar. Whenever we're dealing with really high grade rebars like grade 80 or grade 100, we kind of have to bump that up a little bit. Okay, so those are our 4 factors: the psi T, the psi E, the psi S, and the psi G. What about this stuff on the denominator? Well, this stuff on the denominator is what's called the confinement term, and what it is a function of 2 things, well, really 3 things. But first off, let's talk about the CB term. So the CB term is what's called the bar cover, and it's really just the smallest distance from the center of the tension reinforcement to the closest surface, or the center of the reinforcement to the next adjacent bar. Now we're going to try the pen. I want to see if this works. Let's see. I'm going to draw a little smiley face. Can everybody see the smiley face? Make sure. Check. Yes, yay. Okay, so here's the reason why we use this distance. If you go down to the lab and you actually grip a piece of rebar and start yanking it out of the concrete, what happens is the cracks, they sort of go out in like a radial pattern, like it sort of cracks like this. And it'll keep going out until it hits the first surface. So that might be like that surface right here. And so your failure chunk will sort of look like that. So what we do is we say, okay, what's the closest surface? Well, it's either this distance, and we for simplicity we measure this to the center of the bar. So it's either this distance, it's either this distance, or we say it's halfway over to the next bar, because the idea, if this bar rips out like this, then this one will rip out like that, and so on and so forth. So we just check those 3 distances and take the smallest for CB. So that's a pretty simple calculation. The other term that's a little new is this term KTR. KTR is what's called a transverse reinforcement index, and the way that we compute it is right here. And just so you're aware, a lot of these terms are pretty simple. So ATR is the transverse reinforcement, but if we're talking about a beam, that's just the shear reinforcement. S is the center to center spacing of your transverse reinforcement, but for a beam, that's just the stirrup spacing. And N is the largest number of tension bars in a single layer. So if we were talking about like a situation like this, the N value would be 3, because there's 1, 2, 3 bars. Basically, the idea behind a transverse reinforcement index is that, you've got a beam and it's going off in space like this, and you've got a bar here, a bar here, and a bar here. So let's say you've got those 3 bars. Well, the idea is, again, you're trying to figure out how far you need to embed those 3 bars into the adjacent concrete. And so what also matters is like how the stirrups are performing, because the stirrups are serving to sort of keep all that concrete together. They're confining the concrete around those bars. So more stirrups would mean more effect on your development length. So we take 40 times ATR over S times N. Keep in mind that that denominator, that whole big term, can't be bigger than 2.5. Another thing is that KTR comes out in inches. Okay, so I don't know if that is really too big of a deal, but from your units perspective, because this is in square inches and that's in inches, so there you go. Does anybody have any questions before we just jump right into an example? I've got the infinite recursion going on here. All right, let's get right into an example. So I have here, we're going to determine the development length. Let me get my calculator here. We're going to determine the development length for the 3 uncoated bars shown. So here's the beam, and we're talking about these 3 bars on the bottom, the 3 number 8s. We're using 3 KSI normal weight concrete and 60 KSI steel. And here's the beam, so we're really just going to get right into it. Let me copy this. I'm going to assume everybody can see the calculations. If there's, for some reason, you can't hear anything, let me know. The chat, I can hear the boop, the chat beep. So if you ever have any questions, let me know. So here, we'll call this LD example. Okay, so here's the beam. I'll give everybody a sec to sort of compute some values here, but keep in mind, we do know that this is 3 KSI. We know that this is normal weight concrete. And so because it's normal weight concrete, we know that lambda is 1.0. And then we know that Fy is 60 KSI. Again, I think you're going to find this is really, really simple. Okay, let me get some calculation. I'll be right back. If you ever, I'm going to give you all a sec to jot this down, and then I'll be right back. I think I might have left those in my office, but we'll just do it live. Okay. Let me do this. So here's the formula that we need to compute. So we've already got, you know, if you think we've already got the Fy figured out, we've got the lambda figured out, we've got the FC prime figured out. Help me out. Does anybody remember what dB is? I'm actually going to ask Chad on that. We're dealing with number 8 bars. So if it's number 8 bars, what's the diameter? Does everybody remember how to compute the diameter? If it's, I'll give you a hint. If the diameter is anywhere from a number 3 to a number 8, we do something to compute the diameter. That's fine. Remember, hold on. It's okay. So if you remember, for number 3 to number 8, we take the number and divide it by 8. And so that's 1 inches. 1 inch, I guess I should say. One other thing that's worth mentioning, let me do this. Let me go to course content. So if you go to, I believe I put it in here, you go to new lecture notes. In the new lecture notes and supplements, I put rebar details, and if you open the rebar details, it also lists the diameter of all the rebar. And anything between a number and a number 8, you just take the number and divide it by 8. But I also listed the diameter for all of the other bars as well. So for number 8, 1 inch. Okay. Everybody remember that? I know we're dealing with weird times here, so it's totally fine to miss the little things on that. Okay, so let's look at our adjustment factors. So, get ahead of myself. So we have a psi T, a psi E, a psi S, and a psi G. So let's take each of these one at a time. So let's start off with psi G. Let's remember what the beam looks like. Here, let's remember what let's do this. Let me see if I can copy and paste. Might be a little ugly, but might be easy to follow. All right, so let's start off with psi T. So we're dealing with the casting position factor. So here's our beam. Let's do this. Let's do this. Here we go. I think that might be a little ugly, but it's close enough. All right. So here's the beam. And remember, the psi T is the top bar factor. So we ask ourselves if more than 12 inches is below the reinforcement. Now we're looking at these 3 number 8s, these bars here on the bottom. So if we're looking at the bars on the bottom, help me out. What is the psi T value going to be? Well, no, we're looking at well, okay, yeah. So you're correct that it's less than 12 inches. So if it's less than 12 inches, what's the factor? Tell you what, why don't I do this? This might be a little easier. Give me 1 second. I think what I'm going to do is I'm just going to screen capture all these tables and put them in the notebook. That way I don't have to go back and forth. I think that'll be a little cleaner. There we go. Yeah, I think this is going to work out a little better. Sorry for the clunkiness on today's lecture. I was a little bit in a hurry with the power outage and whatnot. All right. One more. Okay. All right. There we go. So Logan, you were right that the casting position that it would be 3 inches. Now that's not the clear distance because the clear distance we're looking from the bottom of the bar, but that doesn't really matter. The question is whether or not it's less than 12 inches, and it's clearly less than 12 inches. So what I'm asking from Chad is what is the factor if it's less than 12 inches? I want to make sure everybody's paying attention on this. No, it's not. It's not 1.3. It's the other one. See the. Let me blow the table up a bit. So the table says if more than 12 inches of fresh concrete is placed below, then it's 1.3. This is not the case. This has less than 12 inches of fresh concrete placed, so it's 1. Okay. Does that make sense? All right. Okay. Let's take it. Okay, let's take it a little slower. Okay. Now, let me blow this up. Okay, so let's read the table. All right. We're trying to determine our casting position factor. Okay, and I'm gonna read this out. It says if more than 12 inches of fresh concrete is placed below the reinforcement, then it's 1.3. Okay. Now, what we're trying to figure out is the amount of fresh concrete below the reinforcement. What we're looking at are these three bars. Okay. So we're asking ourselves, what is this dimension? And while I mean, we can compute it, but I can just look at it and see it's way less than 12 inches. Yeah, no. We're looking at the three longitudinal bars. And again, I know this is a weird setup, so if you got any questions, please throw them out. Everybody good so far? Okay. What if it's doubly reinforced? Do you use the bottom reinforcements? No, but let me say two things. First off, it's possible that different bars have different development lengths. So you might compute the development length for one set of bars and then a development length for another set of bars. Okay, so that would be my first answer to that question. Second answer would be that right now what we're looking at is the development length of bars in tension. So imagine what we're doing is trying to take the bars and yank on them. If we had a doubly reinforced beam we were looking at bars in compression have a little bit of a different formula, but fortunately that formula is easier. It's much shorter and there's much less stuff going on than with this one. Did that answer your question, Jeremy? That was a really good question. Good deal. All right, let's get back into it. So there's that one. I'm actually gonna make that a little smaller and sort of put that down here. Okay, now let's look at the, so go back here. This is 1.0 because they're bottom bars. So we've got this one taken care of. Now what about the epoxy coated bars? Now, if you remember, here's the table. And the table lists three factors for the bar coating condition. But if you remember at the beginning of the problem, we said that these were uncoated bars. So this is one as well. In fact, what I'm going to do is I'm going to put here some reasons. I'm going to say this is a bottom bar because that covers less than 12 inches. I'm going to say this is uncoated. The bars, the problem said that we were using uncoated bars here. If they were, we would just look at these conditions and determine accordingly. All right. Let me make that one a little smaller, get it out of the way. Next, we look at the bar size factors. So for this, what value are we going to use for our bar size factor? Are we going to use 1 or the 0.8? Exactly. So what I'll say is I'll say 1.0 and say larger than number 6. So number 7 or larger. And then finally, the size of G value. So here's the size of G value. What value are we going to use for our problem? There you go. Like so, and for your default cases, these are always going to be 1. I mean, it's usually the cases that are weird. So we'll say grade 60. Usually the weird cases are the ones where it's not 1. So in the interest of cleaning up the screen a bit, I'm going to delete those tables. So we got that, got that, got that. We know our bar diameters, we got that. So all we need are the CB values and the KTR values. So let's look at CB next. So our CB dimension, I'm actually going to recopy this and sort of move this down here. That's fine. It doesn't matter if it's stretched out a bit. Okay. For the CB dimension, what you do is you look at the bars on the bottom and you ask yourself, what are the following three dimensions? So I'm going to mark the center of the bars. Okay. So the center of the bars, and we're going to ask ourselves the following dimensions. Okay. First off, we ask ourselves what's the distance to the left edge. So these blue dimensions, and they're the same since everything is symmetric. So let me move this over. So they're the same since they're both symmetric. So this is going to be 2.5 inches or 2.5 inches. The next thing we ask is what's the dimension to the upper or lower layer? And what's that one going to be? Because that one isn't clearly given to us. You kind of have to figure that one out. Three. There you go. And then the last thing you have to do is you have to figure out how far is it halfway over to the next bar. So we're talking about these dimensions here. They're all the same. And what are those dimensions? Again, it's halfway over to the next bar, not the whole distance, but half the distance. There you go, exactly right. So this is 1.5 inches, 1.5 inches. So of these three, the 2.5, the 3, and the 1.5, we take the smallest, so C sub B is 1.5 inches. That one's easy. You just take the smallest of the three, because if you start yanking on those bars, you ask, well, how are the cracks going to travel? And this is how they're going to travel. Okay. So next thing we do is we compute the KTR. KTR is our transverse reinforcement index. So we need, here, I'm going to move this over here now. We need ATR, we need S, and we need N. Now, ATR is our transverse reinforcement area. So we're using number 3 U-shaped stirrup. So if I'm using a number 3 U-shaped stirrup, does anybody remember what the area is of a number 3 U-shaped stirrup? It's 0.22. Now what Jeremy said, 0.11. 0.11 is the area of a single number 3 bar. But remember, for a U-shaped stirrup, there's 2 bars. So remember, you take you sort of cut a line this way, and you ask yourself how many bars you go through, and you go through 1, 2. So this is going to be 0.22 square inches. That makes sense? Cool. All right. S is the spacing of your stirrups, and that's given right there on the beam. S is 8 inches. And N is the number of the longitudinal bars. And so what I'll do is I'll say that's 3, because that's our S value, and that's N. All right, everybody clear on that? So if you are, that's everything in this formula. We've got everything taken care of. So here's the formula. So let's just start chugging stuff out. Before I start chugging stuff out, I do want to do one calculation off to the side. First off, I want to do, well, actually I want to do 2 calculations off to the side. I want to do C sub B plus KR over DB. Well, actually, wait, I'm getting ahead of myself because I never computed KTR. Whoops. I'm getting ahead of myself. This new interface for me is taking a little bit of getting used to. So this is 40 ATR over S times N. So that's 40 times 0.22 inches squared over 8 inches times 3. It's number, not inches. And so when you plug and chug that, you get 40 times 0.22 divided by 8 times 3. Hold on. I'm getting 0.367 inches. So in order to compute our development length, I've got to do two calculations off to the side. The first thing I'm going to do is C sub B plus KTR over DB. Okay, so this was 1.5 inches plus 0.367 inches. D sub B was 1 inch, which is 1.867. And the reason why that's important is because this value can't exceed, so I'll say okay, because it can't exceed 2.5. If it does exceed 2.5, we just use 2.5 in our development length calculation. And that does happen when you have, again, some somewhat odd cases. The last thing I want to do is I want to check this factor. This is a little bit of a formality on this problem because these are both 1. And again, that's okay because it can't exceed 1.7. And so therefore, our development length calculation is the following. So we have 3, we have Fy. Fy, I'm going to turn that into PSI because if you look at the bottom, there's a square root of FC prime, and that's got to be in PSI. This is 1, 1, 1, 1, and that's 1 inch. And then we have 40. We have our lambda, which is 1, our square root of 4,000 PSI. And then this denominator that we just computed was 1.867. And so our development length is, drum roll, 38.12 inches. And that's it. Like, that's development length in a nutshell. Can you please go over how you got the dB again? Okay, there's a couple ways to do that. First off, anytime that the bar, so okay, if you go back to this, remember how the bars are number 8s right here? So I'm talking about this number right here. The bars are number 8s. Anytime that number is from a number 3 to a number 8, you can just take that numeral, that number, divide it by 8, and that'll tell you the bar diameter in inches. So 8 divided by 8 is 1. That's one way to do it. Another way to do it is if you go to new lecture notes and supplements, if you remember supplement 3, the rebar details, I listed all of the bar diameters. So this was a number 8, so the bar diameter is just 1 inch. Again, that's why we're here. So I mean, if you got any questions, don't hesitate. I know today's lecture was probably a little clunky because I kept going back and forth, but it's an odd setup. Is there any other questions? Anything I can do to, anything I can address? You can go to the bottom of the workbook again. Yeah. There you go. I'll give you all a second. Then I want to show you something on the homework super quick, and then we'll call it. I'll be right back. You are exactly right, Jeremy. I am so sorry. That is a 0.1 on the mistake counter. Thank you. This is 4,000. That's supposed to be 3,000. This is what happens when you forget your notes. We'll have to figure out an appropriate number there. So this is 3. So yeah, that's wrong. Whoops. Man. 44.01 inches. Woo! What did the chat say on that? 44 for LD. Yep. You're exactly right. We're going to add a full 0.25 on the mistake counter for that one. We're getting close to 7. But fortunately, we only got 5 lectures left. Well, thank you. I appreciate that. You are a nice guy. Any other questions? I want to show you the homework real quick. This is the homework. It's pretty much just a repeat of what we just did. The only thing I'll mention is that's worth pointing out. Number one, this is 3.5 KSI, and I said that it's lightweight concrete. So, I mean, there's a certain factor in that equation that changes whether or not it's normal weight or lightweight. I won't say any more than that because I'm sure you all can figure that out. And then 2, these are these are top bars. Now, I didn't mention it in the beginning of the problem statement, and I'll update this on Blackboard, but these are uncoated bars as well. So we'll treat these as uncoated bars, and they're top bars. Again, lightweight concrete's utilized. I'll update the assignment to show that they're uncoated, but they are uncoated. So this should be a really, really short assignment. What we're going to do next time is, as you noticed, I mean, we got a development length of 44 inches. That's kind of long. So how can we shorten the development length of a bar? Well, you can bend it. So what's the development length of a hooked bar? That's what we're going to talk about on Wednesday. Do the same rules apply even though it's upside down? Yeah, it's just exactly, other than the fact that these are top bars and not bottom bars. So that should affect one of your factors. I'm not saying which, but it's. Any other quick questions I can address? All right. Well, I'm going to go ahead and head on over to steel design. If you aren't in steel design, I will see you all on Wednesday. Again, apologies if the lecture was a little clunky, kept going back and forth, and especially for this infinite thing we got going on here. But next time we're gonna look at the development length for hooks next time, and it's just as simple. It's just as straightforward. For those of you in steel design, I'll see you here in a few minutes. Everybody else, y'all have hopefully try and stay dry and stay healthy. I'll see you all on Wednesday.